Hello everyone, welcome to my next tutorial 1.4 solar cell simulation. As my previous tutorial 1.1 light emitting device simulation, 1.2 electronic OLED simulation and 1.3 white OLED simulation. At here we have concluded number of the specific properties. But in this tutorials I will be simulate at here solar cell properties. So who has not seen it my previous video, please check out. At my first video in the playlist I explain about Fluxim company and they develop software which name Setfos. I have explained all about Setfos software which GUI that give all of the module information. So please check out my playlist video. So now at here, before start of the tutorial, I want to introduce myself. I am Sahil Verma, application engineer of the well-known company Impulse Technology. As move further, I will be explain at here solar cell simulation. Solar cell are semiconductor device which use sunlight to produce electricity. A solar cell or photovoltaic cell is an electronic device that converts the energy of light directly into electricity by means of the photovoltaic effect. We are going to perform or simulate at here. We will present how to perform optical solar cell calculation, active thickness variation, and at here we are given one of the diagrams. So similar diagram we will be made at here Setfos GUI. So let's start our tutorial. We will be open Setfos as run as a administrator. It is a Setfos 5.5 version. New topping models are introduced, so it is given at here. Feature highlight in a Setfos 5.5. The number of Setfos features, so you can check at here. For create new simulation file, you will be click at here. In my first playlist video, I have already explained about all of the toolbars, so you can go and check if you don't know about this. So number of the active layers add given at here. So plus I you can also add more number of layers. Give one by one each layer name which need for the solar cell simulation. Layer top, glass, ITO, PDOT, P3, HT, PCBM. You need one more layer, so add one more layer. Air, hot. Solar cell is surrounded by air, therefore the rename the top and bottom layer of air tops and similarly air bottoms. It is not allowed two identical layer names, so we mention it here tops and bottoms layer. If you want more additional layers, so plus I symbols can be used to more air layer you can add at here. In solar cell calculation, top and bottom layer representing the surrounding medium must be transparent and treated as incoherence. So through the general tab you can activate at here transparency and air bottom is transparent. And we are calculated at here absorption properties, so you need to activate plus symbol of the sun look like absorption module. It can be a transparency, similarly that can be a transparency. At here we noted that convection of the direction of light in coupling in Setfos. The light is always arriving from the active layers. This is also the reflex direction for the calculation of the reflectance and transmittance of the structures. We need to mention at here thickness. So top and bottom layer are semi-infinite medium. So thickness are irrelevant at here because it will be a incoherence. It will be considered 0.5. A unit can also be changed at here. 125 nm for the ITO thickness. PDOT 50 nm. P3HT PCBM 100 nm considered at here, aluminum 500 nm, and it is a earbuds. At here aluminum considered 500 nm, that's layer thickness larger than 500 nm is chosen. The number of calculation points should be reduced to more than 100 point of checking the elements box and entering at here element 100, because if the step is omitted, kernel might be blocked since per default Setfos calculates profile with discrete JSON of each nm as layer of 1 mm require at least 1 million calculation for each wavelength. Be careful with thick substrates and reduce number of elements high resolution not need. That layer which is dependent for the wavelength, so we will be imports at here wavelength refractive index files, that .nk file formats for the ITO.nk file formats, and PDOT we will be supported at here PDOT AL4083.nk file formats. For P3HT PCBM.nk file formats and import at here similarly. For the aluminum at similar we also imports at that file. If you want edit your file, you can edit at here number of parameters and data. If you created your own file, so you can export at here, and real wavelengths graph are showing at here. We will be mention at here air tops refractive index 1 for the glass, it considered will be 0. For element consider 100. Internal quantum efficiency, it is constant. So at here all of the layer structures are completed, so you can check one by one as per your demand. At absorption settings you can shift the wavelength, you can changes at here ranges, it totally depend on you which ranges you want. Intensity scaling not mentioning at here, so you can check at here preview. So all of the layers structures and absorption settings are completed, you can check at script mode. So now you can give your name of the simulation solar cell. You can run at here your simulation, so click the play button, and if you want to abort your simulation you can click at here. So absorption parameters are concluded at here, and you can check at here results for the ITO PDOT P3HT PCBMs. Short circuit currents 10.374. One by one you can check all of the optical profiles, absorption profile, energy flux, generation profile, illumination spectrums. You can click at here wavelength button, you can see at here that variation occur at here. You can see at here the peak illumination spectrum absorption profiles, illumination spectrums, that for the real axis and wavelength. It is a phase, refractive index, white absorption profiles, white spectral absorption profiles, layer absorption also given at here, and absorption. If you want to change at range at here x-axis and y-axis, you can change for ITO, PDOT, P3HTs. Check one by one and transmitted and stacked contributions. Unit you can change as per your choice. Now I am going to simulate active layer thickness variation. So we will be vary the thickness of the active layer P3HT PCBM. So we activate SIM mode and take the parameters of the P3HT PCBMs and their thickness. At the shift settings, we will be give the range 10 to 200 and step consider at here 10 nm. So shift settings are completed at here. So now you can give one new name shift thickness and run the play button and run the simulation. So you can see at here results photo current. You can also check like that for the ITO, P3HT PCBMs, aluminum. Passive active property is also given at here. Reflected transmitted, reflected color are given. Solar integrated absorption, solar eye integrated reflectance, and the transmitted colors. It is a absorption profile. For the all curve you can also check. If you click at here the play button, you can see it here variation according to thickness, layer absorption, glass, ITO, PEDOT, P3HT, and aluminum. Ranges are already given at here. Reflectance, extract contributions, and the transmitted files. It is an active layer, so according to the variation occur at here thickness because you shift that parameters. It is a console view, that value you imported in at here. If you want to change any parameter you can change at here and again you can run your simulation. At here you can see the variation of the short circuit current as previous before the shifts, and at here after the shifts you can see at here the changes. That warning given at here due to large number of the data points as I have already mentioned at here. It is a discretization. So Setfos calculate each nm's calculation. So at here I end my tutorials. I hope you understand my point of view. Get your results at absorptions and shift parameter for the solar cell simulation. If you want more information and if you have any query, please contact us, and my emails and LinkedIn profile also given at description box. So please check it there, and you can also book demo at the impulsetechnology.in. Thank you very much.